Good morning. How are you? I hope everybody is doing well. So today we are going to discuss about SmartPLS analysis, a measurement model, a reflective. So before we start for the analysis, we will try to understand what is the differences between reflective and formative models, and when we are going to use base variance VBSEM or PLS-SEM, in this case SmartPLS, or covariance based SEM or CB-SEM, which is the most famous software for that is AMOS. First, the question to be asked is, what is the structural equation modeling or SEM? So it is a complex models with many associations, incorporate both unobserved or latent and observed variables. So as I mentioned just now, we have two approaches. We have the CB-SEM, which mainly we use AMOS software, and we have variance-based VBSEM or PLS-SEM, where we mostly use SmartPLS. So what is the difference between these two approaches? Basically, the first thing that we need to notice is that using CB-SEM, it is when you are going to confirm the theory, and this is required from you a very strong theoretical justification in order to estimate your model. But for the SmartPLS or the variance-based modeling, it is mainly prediction oriented, so it is more flexible, in theoretical and base. And the distribution of the assumption is, for the SmartPLS, I use SmartPLS for PLS-SEM, and I use AMOS for CB-SEM. So for SmartPLS, the distribution assumption is non-parametric, but for the AMOS is normal distribution or parametric. And also the good things to use SmartPLS is when we have a very small sample size between 30 to 100, and it can be done. But for the AMOS, you need to have a high sample size, at least 100 and above. And the model complexity in SmartPLS is large models is okay, but for AMOS, large models problematic, 50 plus indicator variables. Parameter estimates for SmartPLS is potential bias, but for AMOS is stable if assumption met, and this is one of maybe advantage of using CB-SEM or the AMOS. Indicators per construct, we need one can be run, or two, or even more. But for the AMOS, you need at least 3 indicators, otherwise you cannot run the model. So statistical tests for parameter estimate, we use inference requires or bootstrapping. But for the AMOS, the assumption must be met. And for the measurement model, formative and reflective indicators are okay both together. We can use formative or reflective or mixing both of them. But for AMOS is typically only reflective indicators. So most difficult to use the formative. So why we use SmartPLS or justification? As I say, first it is a prediction and explanation of a target construct. We don't need to have a very solid theoretical justification. Small sample size, complex models, no data normality, support both reflective and formative measurement models as well as a single item construct. And as I say, weaker theoretical support or integration of multiple theories also works with ordinal and binary scale questions, which is all those advantages of using that. So those are the softwares that usually we use to run CBSEM, like AMOS, Literal, M+. And here for PLS SEM we have SmartPLS, PLS Graph, PLS GUI, we have RAPPLS, PLS-PM, SEM-PLS, and others. So PLS path model consists of two elements. We have the structural model and display the relationship between the construct, this construct and this construct. So the relationship between these two, we call it a structural model. And we have the measurement model, we display the relationship between the construct and the indicator. So those are the indicator, relationship between the construct and the indicator, that we call them the measurement model. So as we can see here, a reflective model, you see the arrow going from the construct toward the indicator, while the formative model, the arrow is going from the indicators toward the construct. So what is the difference between the formative model and the reflective model and the formative model? So conceptually, a reflective measurement model happens when the indicators of a construct are considered to be caused by that construct. For example, in intelligence test, if you are more intelligent, you have a high probability of getting the correct answer to the question. Therefore, your intelligence level is predicted, or we predict the score of the question. So the latent variable is the predictor, which is the intelligence. The measured variable or the test is the outcome. The reflective model or reflective measurement model happens when the measured variables are considered to be the cause of the latent variable. So it means that the value, for example, the value of a car is determined by its age, condition, size, brand, correct? If a car is more valuable, it does not turn from a Mercedes into a Ford. Instead, being a Mercedes is a predictor of being more valuable, and value is the outcome. So in a reflective measurement model, we expect the covariances between the indicators to be zero when the latent variable is partialed out. That is the reason that two test scores correlate, is because they are caused by the same thing. In formative measurement model, we don't have anything to say about the covariance of the items. They could be zero, positive, or negative. So formative measurement models are harder to estimate. They are not identified on their own. So let's say, for example, we have this complex model, corporate reputation path model. So here it is an exogenous construct, correct? And this endogenous construct. So this lead to this. And here we have reflective indicator, and you can see the arrows are from the construct or the indicator. And here we have a formative indicator. We have the arrow going from the indicator to the construct. So here what we mean about comp is competence, like is likable, CUSA is satisfaction or customer satisfaction. CUS-L is customer loyalty. QUAL is the quality. PER-L is the performance. CSOL is a corporate social responsibility. ATTR is attractiveness. So this is maybe later we are going to use this model. So this is, we already explained about, the things here. It's the reflective, the arrow going from the construct to the indicator. Indicators must be highly correlated. Okay. And here, formative indicators, arrow going from indicator to construct. So indicators can be positive, negative, or no correlation or zero correlation. So the decision of whether to measure a construct reflectively or formatively is not clear cut. So how you are going to decide? So based, on your theoretical justification. Are you going to use a formative construct or a reflective construct? But remember, reflective is about consequences or trick, and formative is about causes or combination. So those are some of the differences between the formative construct and reflective construct. By definition, a formative is a construct which consists of a composite or multiple measures, and reflective construct is a construct which has observed measures that are affected by an underlying latent and observed construct. So characteristics of the measurement or the items for the formative is uncorrelated or multidimensional, but for reflective is correlated or multicollinear. So for the internal consistency test or Grombacher alpha, not required, but for reflective, not required for formative, but for reflective required to prove convergent validity. So relationship between construct and measurements or items. For formative, changes in the formative measures cause changes in the underlying construct. Items changes means that construct change. But for reflective, changes in construct affect the underlying measures, means change in construct lead item to be changed. Measurement of error in formative at construct level, but in reflective at an individual measurement level. So the effect when items removed in formative may affect the content validity, but for reflective construct will not affect the content validity. And here an example for the formative constructs such as perceived ease of use, perceived usefulness, satisfaction. For this construct, changes in the underlying construct are hypothesized to cause changes in the indicators, meaning that respondent variation in the latent construct of perceived ease of use, for example, will cause all of its measure to reflect this change. An example for reflective constructs such as organizational performance, which conceptualize using three measures: productivity, profitability, and market share. Each measure captures different aspect of organizational performance, where the combination of these variant measures define the construct of organizational performance. So for the measurement model, the goal of reflective measurement model assessment is to ensure the reliability and validity of the construct measure, and therefore provide support for the suitability for their inclusion in the path model. So in order to do the measurement model, so we have to have these two in the reflective, these two most important element, which is reliability, is the extent to which an assumption tool produces stable and consistent result, and validity refers to the extent to which the construct measures what it is supposed to measure. So now I will do some exercises for smart PLS, maybe in an example. So we create a new project. So you just press this new project and we call it project 1. So we press OK. Then you can see we did not insert any data, so we are going to insert the data. So we click on this, correct? Then I will go to data where I want to have or import this data. So for example, my file is here. Okay, you can see the file must be in comma separated value. So if your file is not in CSV, or we call it CSV, then you have to convert that. It's very easy. You just go to a file, save as, then down you check where you find your CSV. For example, let me give an example here. For example, I have this is my file. Okay, so this Excel file is not saved as CSV, right? So I come here, file, save as, over here, right? Then here, Excel book there, I will go here, CSV, comma, delimited. I click here and put save, then put OK. Okay, so now I go back. So I say I click here and go to my file. I click OK, and you can see my data is already imported. You must see this, the green color. If the color is in red, that means there is something wrong with the data. Now you can see here we want to check if there is any missing values. So in order to check for that, we click here and write any number which is not included in your data. For example, -99. Usually we use that number. So -99, I don't have this number in my data. So I press OK here, and you can see I have 11 missing values. So now my data is already prepared. So now we want to have an analysis on estimation. So I click on project 1, and you can see all my data or indicators comes here. So I'm going to off this here, to have more space. Now I want you first to see this is the latent variables, okay, the construct that we're going to build, and this is to connect between them. So in order, let's say, to build model which is let's say this model, I show you here. Okay, I want, for example, to have this model. Competence affect customer loyalty. Competence affect customer satisfaction, and likable also affect customer satisfaction and customer loyalty. So this is could be as a mediator variable, the customer satisfaction. So how I'm going to draw this. So I go back to my project 1. So I say I do this. We have one here, correct? One here. Delete this. Okay. I put a shape. Okay, I bring this down. Then I have another one here, another one here, right? Suppose like that, right? Then I connect between them. We say this connect to this, this connect to this, this connect to this, and this connect to this, and this connect to this. So after that, I put this here again. I will go and bring this. This is, if you remember, we name it. I put right click, rename, and here com, correct? And here again right click, rename, and put like. And here we put customer satisfaction, and here we put customer reality. So now we import all these Latin or indicators to put them in the construct. So I click here, control. So these three, put them here, and you can see they are reflective. Then like 1, 2, 3, put here. Then I have customer satisfaction, or let's see, do this customer loyalty here. Then I have cursor is only one indicator, put here. Now you can see this is, I also can shift it to another one. I just click on it and put here. You can see that one align selected to the right. Sorry. Okay. 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 But now I already draw my model, but you can see some of the cycles are big, some are small. I show you another way how to do it, which is more easier. So I click Control A, all, I delete, and I draw. So you remember, first variable is comp. So I click in the indicator comp, control 3 of them, put here. Second, likability, control, click 3 of them, put it here. Then customer loyalty, put here. Then we have cursor itself only one, I bring it and put it here. Now you can see all my, I change this, align that. Then I come click on connect and connect between this and this, this and this, this and this, this and this, and this and this, which is very easy. Therefore I will rename here, rename com like cursor L. Okay, So my model now ready. So now we want to estimate this model. How we are going to estimate the measurement model. So after drawing the model, I just go here, calculate here. So I click calculate and I put this PLS algorithm. Then I will have here this table. So we have here maximum iterations 300. So you can keep that one, or you can change these to, let's say, 5,000. So here keep it as a path, and we'll start calculation. We start calculating. So now I will have my report, and we are going first to explain all these numbers. You can see here we have so many information is here. This is the past coefficient. If you want to go back to your model first, the first one, and you can see now what's there is the numbers, and you can see this is the loading here, you know, after we are going to discuss about this one. So the first thing is you need to see is that as I say, this is a theoretical model with a result like loading R square coefficient. Now you can see this 0.562, and this means that the three exogenous construct together, which is comp, like, and CUSA, these three explain 56.2% of the variance of the endogenous construct, which is customer loyalty. Therefore, the R square equal to 0.562. So comp and like together, comp and like, these two together, how much explain? How much these two explain with this and this? Explain 29.5. This 29.5. This comp and like explain 29.5% of CUSA or customer satisfaction. So the structural model result enable us to determine, for example, that CUSA has the strongest effect on customer loyalty by 0.504 here, followed by like 0.342, then followed by comp is only 0.009. Also comp and like predicting the CUSA or customer satisfaction. First, like, it has the strongest effect on CUSA with 0.424, followed by comp is only 0.62. Again, this here 0.009, 0.162, 0.5, that's what we call the path coefficient or values, you know, measure the relationship between the construct, between this construct and this. But here, these numbers here, or this, or this, or we call them relationship, correlation between construct and items, correct? Or we call them the factor loading. Those numbers, they must be above 0.7, otherwise they are not loading. So if they are below 0.7, then you have maybe to draw that items or do other necessary things. So here I go back and I see path coefficient here, and those numbers which are same like in this graph or in this model. Also you can get them as in table. So now I will go and click on the auto loading, and you can see these are the loading or the indicators or the items or relationship between the construct and the indicators. So you can see all of them are green, so that means above 0.7. If it is below 0.7, it will show in red color. So you can see, so we can say all auto loading of the reflective construct are greater than the minimum threshold value of 0.7. So now the question is it that all these coefficients are statistically significant? So how to determine if these indicators or coefficients are statistically significant? So here we are going to run the bootstrapping. So what is it? Bootstrapping in statistics, bootstrapping can refer to any test or metric that relies on random sampling with replacement based on Efron and Shirani 1993. Also, bootstrapping allows assigning measures of accuracy defined in terms of bias, variance, confidence intervals, prediction error, or some other such measure to sample estimate. Also, it may be used for constructing hypothesis tests. It is often used as an alternative to statistical inference based on the assumption of a parametric model when that assumption is in doubt, or where parametric inference is impossible or require complicated formula for the calculation of standard error. So what are situations where bootstrapping is useful? So first, when the theoretical distribution of a statistic of interest is complicated or unknown. Therefore, since the bootstrapping procedure is distribution independent, it provides an indirect method to assess the properties of the distribution underlying the sample and the parameters of interest that are derived from this distribution. Also, when the sample size is insufficient for a straightforward statistical inference, bootstrapping provides a way to account for the distortions caused by the specific sample that may not be fully representative of the population. Also, third, when power calculation have to be performed and SmartPLS sample is available, the power calculation binary hypothesis test is the probability that the test correctly reject the null hypothesis H0 or H9 when the alternative hypothesis H1 is true. Most power and sample size calculations are heavily dependent on standard deviation of the statistic of interest. In the same, if the estimate used is incorrect, the required sample size will also be wrong. One method to get an impression of the variation of the statistic is to use small pilot sample and perform bootstrapping on it to get impression of the variance. So this was were cases to use. So now we are going to use the bootstrapping again I put calculate, right, bootstrapping, and here 500, I put it 5000, better. So here I click complete bootstrapping, yeah, and you just press start. So here remember the subsample, the recommended is 5000, huh? So now it's calculating. We wait until the calculation is done. Okay, so now I have my statistical result, the significance. And you can see here all of them are significant, only one from competence to customer loyalty, which is insignificant. The p-value is 0.867 and it is in red. Usually when it is in red, it's not significant. So what I do now, I will click here to access the significance level of the auto loading. So I put here auto loading, right? I click here, then I will have this, and you can see all the indicators are significant. See the p-values here, all 0.00 and in green color. So here the t-values or t-statistics. So the t-value and p-values for the measurement and structural model estimate are used to evaluate the significance level. So if it is below p-value below 0.05, we can say it's significant at 5% level. And here this original sample, or so they are the initial model loading, and this sample mean here, I click here, sample mean here, are numbers, the average of the bootstrapping subsamples estimate of outer loading. Okay, so how we are going, also we have this confidence interval. I click on it to obtain confidence intervals. It shows that 95% confidence level here. Then how now I go back here to my original one. This is the mean STDV, t values, p values. How I'm going to explain that. So I start here. So we have the t values and p values of all hypotheses, as we can say, as we can see here, are highly significant at 0.01 significance level, which is 1%. All items used are relevant and should be retained in the model. If something here is below 0.7 here, it shows that it's not significant here. It shows that it's more than 0.05. So you have to remove that items, or you have to correct it. If you are already collected the data, you cannot go and collect the data another time. So this item that need to be deleted. So that it is advisable that when you collect the data, at least construct at least 5 items or questions, or what we call them indicators. So if you have one or two of them is not loading, so you can take them out of the model and you still have remaining 3. But to do so, to remove the items, make sure that you don't remove more than 20% of the total items. So if your construct have 5 items, so the allows you to remove only 1, which is concept of 20%. if you have 10 items, then you can delete 2. So maximum 20%. So the t-values can be compared with critical values from the standard normal distribution to decide whether the coefficients are significantly different from 0. For example, the critical value of the significance level of 0.01 and 0.05 probability of error are 2.57 and 1.96 respectively. This is when we use two-tailed test. For one-tailed test is for 0.05 level of significance is 1.65. So we can see here our t-statistics all above 2.57. So that it comes, p-value is almost 0, you know. Now I go back to my model, and you can see here I can change this. You see here, this is like this t-values, right? The inner, right? So I can put them p. Sorry, here outline. See? Up. P. See? Become 0, 0, 0. So this 0, 0, 0 here, 0, 0 here, they are here. This. So if I want to put them t, I put here t, and become, you can see 42.400, and it is here, right? The statistic, yeah, for comp 1. Okay, so it's up to you if you want the inner here. Now is p, but use this significant, significant, right? Only this not significant. You can see it here. Path coefficient, yeah, 867. Comp to customer loyalty. This comp to customer loyalty is 0.867. Okay, so you can change them from here. So now we go to the second criteria, which is the composite reliability and of the our model. So I go back here. Okay, I go to Grombash Alpha here. See, I click Grombash Alpha, and again I will have this is, it will not indicate because it's only one indicator, remember. So I have, see, all my customer loyalty and like are significant, 0.00. So means that, see, all of them above 0.7, the loading here. So that one, all reliabilities here are well above 0.7. And as I say, this one here, CUSA or customer satisfaction, do not interpret the one. For CUSA, it is a single item construct and internal reliability is not relevant. Okay, then I go now to average variance extracted, or AVE. Where is it? Here, click on it. Okay, and I see again here some of the values. You can see here all the AVE values are above 0.5. So the requirement for the AVE is 0.5 and above, or we call it convergent validity. So what is it? Convergent validity is a parameter often used in sociology, psychology, and other behavioral sciences, which is referred to the degree to which two measures of construct that theoretically should be related are in fact related. Convergent validity, along with discriminant validity, is a subtype of a construct validity. So same here, we do not interpret number one, this one. For the CUSA, it is a single item construct. So internal consistency reliability, we have two. First, as we see, we have the composite reliability, or CR, must be above 0.7 in exploratory research, and between 0.60 to 0.70 is acceptable with justification. Grombash alpha must be above 0.7, and we have the indicator reliability, the squared loading, or the proportion of indicators variance that is explained by Latin variables, and also these must be above 0.708. For the converger validity, we have the average variance extracted, AVE, it must be greater than 0.5, I just explained. And the last, we are going to see, we have discriminant validity, we have the Fornell-Lacker criteria, cross-loading, and HTMT criteria. So, how to go now for discriminant validity of Fornell-Lacker? So again, I will click on this here. Discriminant validity, where is it? Right, okay. I put up here also. Okay, let me put this up. Okay. I think, where is it? Composite. Okay, I go here. Yes, here. Algorithm. This is discriminant validity. So, I have this table. How we are going to explain that? So, in discriminant validity, you must have first this competence. The value, it must be greater than all these values. Means that if you see here, we found that the result here indicate that discriminant validity between all construct there is. See here, 0.825 is greater than all this. 1 is greater than the other. 0.86 also greater than this. So we can see, for example, for COM, values are greater than COSA, COS-L, and like values. And COSA value is greater than COS-L and like values. And COS-L value here is greater than like value. So we can say that discriminant validity between all constructs is there. Discriminant validity, again, it is a test whether concept or measurement that are not supposed to be related are actually unrelated. So this is the definition of the discriminant validity. So now we go to a cross-loading here, okay, and say here we have the indicator, how we are going to determine if discriminant validity is here valid. So you can see here the lower, for example, we take count 1, 2, 3. The lower value of count, which is here 0.798, it must be greater than all values of the other one indicator or variable. Correct? So you can see here 0.798 is greater than COSA, 0.4, this, all. And for COSA, which is 1, automatically is greater than all of them. For COS-L, these 3, 1, 2, and 3, right? So what is the lower one? 0.833. I can check here. Yes, greater here all. And yes, greater than this all. And the last like, which is the lowest value here, 0.843, which is yes, greater than all these values. Of course, except these two, because it's related to like, right? So we don't consider these two. So the result indicate that there is a discriminant validity between all indicators. Now I also click on HMTM. So here we have all values are in green color. So all values in green color means that there is discriminant validity. If the value is in red color, then there is no discriminant validity here. Okay. Then what is discriminant validity or HTMT? HTMT is the ratio of the within construct correlation to the between construct correlation. Within and between. So technically, HTMT approach is an estimate of what the true correlation between the two constructs would be if they were perfectly measured, i.e. they were perfectly reliable with no error. So what are the rule of thumbs? All HTMT values should be lower than 0.85 for constructs that are conceptually distinct, such as work environment, perception, and organizational commitment, or brand equity, performance, and you can see all of them here is below 0.85, so that it is in green color. But also, all HTMT values also should be lower than 0.90 for constructs that are conceptually more similar. For example, like such as customer satisfaction, loyalty, organizational commitment, and job satisfaction. So, for example, here we have customer satisfaction, loyalty here, right? If our, let's say, number shows 0.89, which is below 0.90, right? Still consider, yes, significant, or there is HTMT or discriminant validity. Confidence interval for HTMT values for the structural path containing the value 1, okay, indicates a lack of discriminant validity. Conversely, if the value 1 falls outside the interval range, this suggests that the two constructs are empirically distinct. For example, I will check here, and you can see all of the HTMT values are lower than 0.85, 0.9. Also, I will go to this, click here, bootstrapping, okay, I click HTMT, okay, and you can see here, these two here, none of the confidence interval include a value of 1. See, there is no 1 here. Okay, so hence discriminant validity is demonstrated by the HTMT method. So what to do if any of these HTMT criteria indicate a lack of discriminant validity? First approach attempts to increase the average within construct correlation and or decrease the between construct correlation of the construct measures. To decrease the average between construct correlation, what you can do is first eliminate items that are strongly correlated with the items in the other construct. Or number 2, reassign these indicators to the other construct if theoretically possible. It is important to note that the elimination of items purely on statistical grounds can have observed or adverse consequences for the content validity of the construct. Therefore, this step entails carefully examining the skills, either based on prior research results or on those from a pretest in case of the newly developed measure, and determining whether all the construct domain facets have been captured. The second approach attempts to merge the construct that caused the problem into a more general construct. Again, measurement theory must support this step. The result would be the more general construct replaces the two problematic constructs in the model. So this step may entail modifications to increase the construct within the construct correlation and or to decrease the between construct correlation. So again, I will give you some rules of thumb for evaluating reflective measurement models before we end. So internal consistency reliability or composite reliability should be higher than 0.7 in exploratory research, and could be between 0.6 to 0.7 is considered acceptable if you have a valid justification for that. Consider Bromwich alpha as the lower bound and composite reliability as the upper bound for internal consistency reliability. Indicator reliability, the indicator outer loading should be higher than 0.7. Indicators with outer loading between 0.4 and 0.7 should be considered for removal only if the lesion lead to an increase in composite reliability and AVE above the suggested threshold value. So convergent validity, the AVE should be higher than 0.5. Discriminant validity, use of HTMT criterion to assess discriminant validity in PLS-SEM. The confidence interval for HTMT statistics should not include the value of 1 for all combination of construct. According to the traditional discriminant validity assessment method, an indicator outer loading on a construct should be higher than all its cross loading with other construct. So furthermore, a square root of the AVE of each construct should be higher than its highest correlation with any other construct, or this is the Fornell Lacker criterion as we just now explained. So by that we have done the first part, which is the reflective measurement model. I will see you in part 2 where we do the formative measurement model. Thank you very much.